What is up, Matt Superstars? In this edition of Mr. Peterson Presents, we are going to be talking about how to determine probability. And so in this lesson, we're going to do a brief review of how to determine probability. And then we're also going to get into the difference between theoretical and experimental probability. So just a quick recap, you've probably seen this since about 4th grade. So we got some fill in the blanks. The closer the probability is to 1, the more likely that the event will happen. And if the probability is getting closer to 0, the less likely an event will happen. And so if it's something that's more likely to happen gets closer to certain, is that the sun will rise tomorrow. For ones that are less likely to happen, asteroids slamming into the planet. So we got lots of different ways we can determine probability. Obviously, give us some very extreme examples, but probability is a lot of fun in playing games, but also determining different things happening. So the way we write probability, you're going to see this format a bunch. So it has the P of an event. So it might be the probability of pulling a card, probability of getting a king, or the probability of an ace. So you'd write the probability of an ace. You might say the probability of getting an A on the spinner, or the probability of getting a B on the spinner. So what we just write that event happening is we're going to write that as a fraction. So the fraction goes is the denominator is the number of possible outcomes in the sample space. And for your numerator is the number of favorable events. And so we have a couple examples here. In example number 1, there are 6 equally likely outcomes on a spinner. Find the probability of B. So we're looking for the probability of B. Our denominator is going to be the 6 sides on the spinner. And of spinning a B, there's just one B, so we're just going to write that as a fraction, 1 out of 6. So for number 2, probability of finding a consonant. So what we do is we have to write it in this format if we're doing probability. Denominator is still the same, but we have to count up our consonants. So B, C, D, and F. So we have 4 consonants here, so we have 4 6. When we simplify, that is going to simplify to 2/3. And so I can say the probability of finding a constant is 2 out of 3. So here's number 3. If I roll a number cube, so my 6-sided dice, and so we got to find the probability of each event. So the probability of rolling a 3, there are 6 sides, and there is only 1 3, so you can write that as 1 6. And to find that as a decimal and a fraction, our decimal is 0.16167 because the 6 repeats, but I'll round it. And for the percent is 16.7%. What's the probability of being greater than 4 on my spinner? And so on my dice, I'm sorry. So the dice, there's 6 sides, greater than 4. So 4 is not included. So we got 5 and 6 are the two that I'm looking for. So I have 2 6. So my probability after I simplify is 1 out of 3. So I can say that that is decimal 0.333, and it repeats forever. And there is a 33.3% chance of this event occurring. So how about a probability of an even number? Denominator still 6, and we just count up our even numbers. So 2, 4, and 6, so there's 3 of those. When I simplify, it simplifies to 1/2. So I can say that the probability of getting an even on the dice is 1/2, or I can write that as 0.5 as a decimal, or you have a 50% chance of that actually happening. So how about this problem here? So one letter tile is selected and then the spinner is spun. What's the probability that both are going to be a vowel? And so the way we're going to look at this is we need to find the probability of each event happening, and then we had to somehow combine them to figure out the probability of both of them happening at the same time. And so the probability of selecting a vowel from the tiles, so we have 1, 2, 3, 4, 5, 6, we have 7 tiles. And we're going to find our vowels. And so we have E and A. So we say the probability of selecting a vowel is 2/7. And then the probability of spinning a vowel, so we have 6 on the spinner. And our vowels are A and E is 2/6 or equal to 1/3. And so we have our two different probabilities here if we play the game separate. But if we're going to combine these together, what we're going to do is we're going to multiply our fractions together to figure out the probability of both events happening, because that's what we have to figure out right here. So for that to happen, we have 2/7, and then we multiply it by 1/3. So make sure you multiply it by the simplified part. And then what we do is we multiply across on our fractions. So multiply our numerators together is 2. Multiply their denominators together is 21. So I can say that for both getting a vowel in both games, there's a 2 out of 21 chance of that occurring. So you can kind of see if you're creating a game, say if I was creating a game for a carnival, I'm going to try to increase my number in my denominator, make it more challenging. And so the game is actually pretty easy if you just have to pull a vowel from the bag of tiles, or if you have to spin a vowel. But if you make both, then you see the game is a little more challenging and less likely to happen. So now, from the previous example, what happens if both letters are A? So the probability of pulling an A and spinning an A. And so we're going to do 1/7 times 1/6. And that's going to give us a 1 out of 42 chance of happening. So you can see this is even less likelier to happen. But the probability of both consonants. So if I'm going to let's circle my consonants here. So I have G, B, S, L, T. So there's 5 out of 7. And for spinning a consonant here, so I'm going to circle my consonants B, C, D, and F. So that's going to be 4/6, which is equal to 2/3. And that's what I'm going to multiply the second fraction by. And then I multiply my numerators, multiply my denominators to get 10 out of 21. So you can see that game B is more likely to happen. It's the easier game to play if I'm going to be playing these two games. So now let's talk about the difference between theoretical and experimental probability. So in theoretical probability, as you fill in the blank, this is determining what should occur. So before we actually play the game, we can kind of figure out what are our chances of winning. And so this is exactly the same setup of what we did, and just figuring out what's the probability before even playing. So in experimental probability, this is where it changes here, because this is what actually occurred. So if you played the game several times, what actually happened? And so the way we write this is similar to the setup is the probability of an event. This is going to be, the numerator is going to be the number of outcomes that occurred. So if you're trying to do the spinner, how many times did it actually land on a letter? Or how many times did you roll a number? And then our denominator is the number of trials performed. So how many times did you actually play the game? Did you play the game 5 times, 10 times, 20 times? Did you play it 1,000 times? And what actually happened when you played that game 1,000 times? So here we are given this table below that shows the results of spinning our spinner right here of awesomeness. Our spinner is divided into 8 equal sections to make sure the game is fair. And so here you can actually see right here we're given some data. This data, anytime you see the data and it has the frequency that something happened, this is going to be your experimental data. So in my experimental data, I can see how many times that you spun a certain number. So I can see that in spinning a 5, that was spun the most times at 10. And for some reason 8 only got 3 hits on it. And so in order to figure out the number of times that you played this game, what you're going to do is you're going to add up all of the totals in the frequency table. And so you're going to do 8 plus 3 is 13. 13 plus 9 is 22. Plus 4 is 26. Plus 10 is 36. Plus 6 is 42. And then plus 5 is 47, and then plus 3 is 50. So I can say that this game has been played 50 times. So in determining that, that's going to be your numerator for your, or denominator, I'm sorry, denominator for your experimental data. So now we're given this question. We need to find the theoretical and experimental probability for landing on 6. So in order to do this, the theoretical is the one we're used to all the time. So we know that there's 8 sections on our spinner, and there's only one spot for a 6. And so I can say that you have a 1/8 chance of landing on 6, or if I converted that to a decimal, is 0.125. Then your percent is you have a 12.5% chance of this event happening. If I figure out the experimental data here, denominator is going to be 50. We landed on 6 times. And so what we can do is we can simplify this to 3 over 25. But let's get that into a decimal, and let's see how close we are to this actually, the theoretical and the experimental, see if it matched up at all. So if I do 3 divided by 25 in the calculator, I can get a decimal of 0.12, or I can get 12%. So I can see that my experimental data is really, really close to the theoretical data. And so in experimental, the more times that you play this game, the closer and the closer you should get to this theoretical data. So now, based on the experimental probability, how many times would you expect the spinner to land on 3? So in order to kind of decode this type of problem, what we're going to do is we're going to set up the probability of landing on 3 using our experimental data here is what we're trying to figure out. So denominator is out of 50, because we ran the trial 50 times. And the spinner, we spun a 3 9 times. So there's our fraction that we're going to start with, 9 over 50. And if we spin the spinner 100 times, we need to figure out what our numerator is going to be. So if we did this, we can multiply by the same factor in the numerator and the denominator. So 50 times 2 gives me 100. 9 times 2 gives me 18. So I can say that if I spun the spinner 100 times, it would land on 3. It would land on 3 18 times out of 100. What happens if I spun the spinner 200 times? So same thing, I would set up my original fraction, 9 out of 50. And now it's out of 200 times. So you can multiply the top and the bottom by the same factor here. So I set it up x over 200. So 9 times 4 gives me 36 out of 200. So I can say that the probability of landing on 3, if I spun it 200 times, is going to be 36 out of 200. And so you can see here, there's a couple of different ways you can do this. The way I'm doing it is I'm multiplying the numerator and denominator by the same factor, or you can just cross multiply, just like solving a proportion. What happens if the spinner spun 25 times? So 9/50 is equal to x over 25. So this one is, you can obviously divide the numerator and the denominator by 2, because 50 divided by 2 gives you 25. So whatever you do at the bottom, do at the top. For this one, I'm going to cross multiply so you can see how I can cross multiply here. So I can do 50x is equal to 25 times 9, gives you 225. And then I just divide both sides by 50 to get x by itself. So I can get x being equal to 225 divided by 50 to give me 4.5. And so I can say that if I spun the spinner 25 times, it's going to be 4.5 out of 25. And so it's going to be somewhere between 4 and 5 times that, if I did the experiment, should happen.